Hi everyone, we are ready to start. Welcome to Neurotechnology's webinar, and today we'll be talking about the human-machine interactions, and specifically we'll be investigating stress patterns in human-robot interactions through EEG analysis. I'm very happy to welcome our guest speaker. We have today with us Simone Borghi. Hello, good to have you here. So just a little housekeeping before we get started. We'll begin with Simone's presentation with the duration of about 40 minutes, and this will be followed by Q&A. So please feel free, as always, to submit your questions at any time using the Q&A tool. You will see here on the bottom of Zoom tools, the Q&A. And for your information, the recorded version of this webinar will be also available offline on our YouTube channel. Actually, all previous webinars you can find there as well. Okay, so please let me quickly introduce our speaker. So Simone Borghi is from the Department of Industrial Engineering at Unimore University in Modena, Italy. And he brings an expertise in industrial biotechnology. His research has been primarily focused on the design and development of biosensors utilizing organic polymeric semiconductors for the real-time detection of COVID-related biomarkers, notably interleukin-6. So this was like in the previous pandemic and pre-pandemic period. And his current research focuses on the analysis of human stress within the industry landscape. So he's leveraging state-of-the-art sensor technologies, and this includes EEG, ECG, galvanic skin response, electrodermal response, eye tracking, facial expression, and body gesture. All this for the analysis of human stress. And his research is centered actually around developing methodologies and tools to accurately detect and monitor stress levels of operators in real time via modern wearable biosensors, I was mentioning in a few seconds ago. And by doing this, he aims to adapt platforms and production processes, optimizing workflow, mitigating potential negative impacts on the well-being of operators. And not only from the academic point of view, but also from the real practical applications, addressing the real world challenges faced by industries today in the complexities of human-robot interactions and industrial ergonomics. So Simone, thank you for being with us. The stage is yours.
Thanks. Hi everyone. My name is Simone Borghi from Italy. Today, I'm thrilled to address a topic that sits at the intersection of human cognition and technological advancement, investigating stress pattern in human-robot interaction, HRI, in particular, but also in the full context of Industry 5.0, through EEG analysis and outer psychophysiological signals. In our rapidly evolving world, the interaction between humans and machines had become increasingly commonplace. However, as we embrace that advancement, it's crucial to understand how they impact us on a fundamental psychophysiological level, including our stress response. Stress is a universal human experience influencing our thought, emotion, and behavior. For example, in the context of human-robot interaction, stress can arise from various factors. For example, uncertainty about the robot intention, complexity of the programming procedure, or simply the novelty of the interaction itself. Understanding how individuals experience stress during the interaction with new technology is essential for designing applications that enhance rather than diminish their human role in modern society and its well-being. This is where EEG and in general biosignal analysis come into play. So a bit about me, of my academic achievement I attained at the University of Modena Reggio Emilia, Unimore. My educational journey at Unimore began as a bachelor degree in biotechnology, where I delved into biosensor based on organic semiconductor. Building upon this foundation, I pursued a master's degree in industrial biotechnology at Unimore, My master thesis covered the research on the specific sensing of interleukin-6, an inflammatory biomarker using organic electrochemical transistors. In addition to my formal academic pursuits, I also engaged in supplementary training throughout the master in data analysis, statistics, machine, and deep learning. Actually, I am at the second year Ph.D. at the Department of Industrial Engineering at HRI Modena. Within our C-Lab laboratory, we are actively exploring the integration of virtual and augmented reality technologies in industrial context. This cutting-edge technology offers an opportunity to enhance workplace safety, productivity, and user experience by providing immersive and interactive environment for training, design evaluation, and task execution. By simulating work environment and tasks in virtual and augmented reality, we can assess ergonomic risk, identify potential hazards, and iteratively refine design to improve use comfort and efficiency. In particular, my research is centered around developing methodologies and tools to accurately detect and monitor stress level of operator in real time via modern wearable biosensors. By doing so, we aim to adapt platform and production process dynamically, optimizing workflow and mitigating potential negative impact on the well-being of operator. This endeavor is not merely an academic pursuit, but a practical application as technology to address real-world challenges faced today by industries. So, thanks to Neuroelectric for providing me with the opportunity to participate in this webinar. Now, let me outline how this webinar will unfold from start to finish. We will begin by exploring the concept of Industry 4.0 and its evolution, Industry 5.0, and its implication for modern industrial practices. This will provide a foundational understanding of the technological advancement driving the transformation of industrial processes. Next, we will delve into the crucial role of human factor in Industry 5.0. By understanding the interaction between human and technology, we can unlock the full potential of human technology and human robot, for example, also human-robot collaboration, while ensuring the well-being and productivity of human operators. We will then drift of focus on the phenomenon of stress and its significance in industrial setting. Stress can impact performance, safety, health, and overall job satisfaction, making it essential to address. Finally, in the main part of the webinar, we will explore the use of EEG technology in stress evaluation and possible strategy for using brain signal for statistical analysis and possible machine and deep learning technique in stress evaluation, as well as possible data labeling strategies. So the number 4 for Industry 4.0 stands for the fourth industrial revolution. The first industrial revolution, characterized by mechanization and the advent of steam power, transformed manufacturing processes and propelled humanity into a new era of productivity. The second industrial revolution introduced mass production techniques, epitomized by the assembly line, and harnessed the power of electrical energy to drive unprecedented level of output and efficiency. With the dawn of third industrial revolution, automation, the countertop of industrial progress, computers and electronics emerge as transformative tools, enabling the optimization of processes and the integration of complex systems. Now, we find ourselves at the cusp of Industry 4.0, where cyber-physical system, Internet of Things, interconnected network redefine the very essence of manufacturing and production. In this era, machines are not merely automated, but imbued with intelligence capable of autonomous decision-making and seamless communication with one another. For example, going into more detail about modern technology of 4.0, Internet of Things, that refer to interconnected network of physical devices, vehicle, appliance, and other items with sensors, software, and connectivity that enable them to collect and exchange data. These devices can communicate with each another and with a centralized system, allowing for seamless integration automation for various processing. Artificial intelligence, that is a branch of computer science focused on creating systems that can perform tasks that typically require human intelligence. AI systems are designed data, recognize patterns, make decisions, and learn from experience, often mimicking human cognitive functions such as problem solving and decision making. AI technologies include machine learning, natural language processing, computer vision, robotics, among others, and it finds application across different fields, including healthcare, finance, transportation, and entertainment. Virtual reality and augmented reality for Industry 4.0 are immersive technologies that alter our perception of reality by overlaying digital information into the physical world or by creating an entirely virtual environment. In virtual reality, users are completely immersed in a simulated environment generated by computer technology. By wearing VR headset, users are transported to digital realms where they can interact with virtual objects and environment in a seamless, real way. VR is commonly used in entertainment, gaming, education, training simulation, industry, and virtual tours. Augmented reality, on the other hand, enhances the real-world environment by overlaying digital context, such as images, videos, or 3D model, into the user view of the physical world. AR technology is typically experienced through smartphone, tablet, or AR glasses. Robotics, on the other hand, is a field of engineering computer science that involves the design, construction, programming, and operation of robots, autonomous or semi-autonomous machines capable of performing tasks traditionally carried out by humans. A robot can be designed to perform a variety of functions, such as assembly line tasks, surgical procedure, exploration in hazard environment, or assistance to people with abilities. So, great. All these technologies are exciting and wonderful, but faced with this and other new and impressive technologies advance on may wonder, what is the role of man, of the human in all this? In fact, we have the impression, but also the fear that with the power of technology, human may be overaimed or indeed no longer used for the risk of being excluded completely from the working context. For this reason, in the transition from Industry 4, where system efficiency reigns supreme, to the dawn of Industry 5.0, we are compelled by the imperative to prioritize the well-being and needs of individuals within industrial processes. While Industry 4.0 revolutionary manufacturing through automation and data exchange, it often places a disproportional emphasis on optimizing system efficiency at the expense of the human-centric considerations. Recognizing the limitation of this approach, Industry 5.0 emerged as a necessary evolution, a paradigm shift toward a more holistic and inclusive industrial framework. By integrating ergonomic principles, personalization interfaces, and adaptive technologies, we strive to create environments that are not only efficient, but also conducive for the well-being and flourishing of individuals. Following this paradigm, the representative technology of Industry 5.0 and the importance of the human at the center of everything are human-robot interaction system, human cyber system, and user adaptation. In fact, powerful and innovative technologies such as robotics, Internet of Things, virtual augmented reality, artificial intelligence, described above, while capable of incredible feats, ultimately rely on the user acceptance and adoption. If they are not perceived as useful, friendly, and easy to use by the end user, risk become obsolete despite their potential. By placing the needs, preferences, and experience of user at the forefront of technological development, we can ensure that this technology not only fulfill their intended purpose, but also enhance human well-being and quality of life. After all, the true measure of success for any technological innovation lies in its ability to empower and enrich the lives of those we interact with it. In fact, there is not adhering to that principle is epitomized by the protagonist of the film Modern Times, portrayed Charlie Chaplin. It's not coincidence that this worker is afflicted by high level of stress, something that we may now term as burnout. In the film, technology is not perceived as helpful, but rather as something that dominates and dictates the true pace of the progress, often overshadowing the human operator. Work is perceived as alienating, something over which one has no control, and it's only a source of anxiety and stress. This cautionary tale serves as a poignant reminder of the potential pitfall of technological advancement, what needs and well-being are overlooked. As we navigated the complexity of modern technology, we must strive to ensure that innovation is driven by human-centric approach, empowering individuals and fostering a symbiotic relationship between humans and machines. This graph paints a compelling picture that appears to resonate with the reality. Stress is indeed ubiquitous, transcending graphical and cultural boundaries. According to the data, approximately 10% of the staff across all nations report experiencing chronic level of stress at work. This staggering statistic underscores the pervasive nature of stress in modern society, highlighting the urgent need for effective intervention and solution to address these pressing issues. As we delve deeper into our exploration of stress patterns in industry, it is essential to acknowledge and understand the broader context of stress prevalence, recognizing its impact on individuals and society worldwide. So, with this aim, the paradigm of Industry 5.0 is human at the center of the entire production system, of which I think the quote of Olivetti, a great and visionary Italian industrialist of the last century, is very powerful. In fact, the goal is to empower human workers and enhance their capabilities, creativity, and well-being. In this context, technology serves as a tool to augment human skill, increase efficiency, and improve health and working conditions. This human-centric approach not only fosters greater acceptance and adoption of new technologies, but it also ensures that benefits of the Industry 5.0 are realized by all stakeholders, leading to a more sustainable and inclusive future of manufacturing, production, and industry. So, how can we really put human at the center of the production system and design adaptive technologies? To do this, it is crucial to monitor psychophysiological state in real time using modern biosensors, aiming to collect high-quality data signal to classify and possible predict stress state or other psychophysiological conditions, such as physical fatigue or cognitive workload. Here in the figure below are some examples of modern biosensors presented in my lab, such as facial motion recognition with computer vision AI algorithm, skin electric activity monitoring with Empathia, eye activity with eye tracking, and earth activity with electrocardiography. Of course, the brain is a complex organ serving as the source of decision-making, creativity, and cognitive processes. Metrics extracted from the brain signal are undoubtedly among the most powerful in defining state of stress. Studies delve deep into the intricacy working of the brain, employ various techniques such as electroencephalography, functional magnetic resonance imaging, and positron emission tomography, scan to monitor neural activity associated with stress. By analyzing a pattern of brain activity, researchers have identified specific neural signatures and biomarkers that correlate with heightened stress levels. On such metrics that have gotten considerable attention in the measurement of brainwave frequency, particularly in the beta, gamma, and alpha frequency range. We'll cover this in much below. I have personally carried out studies on stress assessments in human-robot collaboration and programming context using a modern 20-channel Nobio helmet from Neuroelectrics. So about stress, but what is stress? We have all experienced stress and we could all intuitively explain it. However, if we think about it, finding a precise definition is not. How can it be quantified? How stressed we are compared to another situation? According to World Health Organization, stress, and in particular acute stress, is a natural reaction to a dangerous or perceived dangerous situation. So it can be anxiety toward the future, toward a situation, and in our specific context, toward the use of a technology, for example. It is a natural and absolutely non-harmful in itself. Indeed, as we discussing in the following slide, fundamental in our evolutions. It becomes harmful if it continues beyond the presence of the stimulus in an undetermined manner, or is disproportionate to the situation, the so-called chronic stress. A chronic level of stress can lead to pathological states such as cardiovascular and mental problems. So there are many definitions of stress. The Finn Cannon's fight or flight response theory to be the most accurate in understanding metrics useful in assessing stress. The fight or flight response is a fundamental psychophysiological reaction triggered by the perception of threat or danger. It is an evolutionary mechanism that has been finely honed over millennia to help organisms survive immediately perilous situations. When confronted with a perceived threat, whether real or imagined, the body undergoes a series of rapid and coordinated change to prepare for either confronting the threat, fight, or free from it, flight. We can add a third type of reaction, which is freezing. Note that this reaction is not guided by cognition or reasoning, but occurs before a rational decision. This reaction to danger was fundamental to our evolution. It could be said that without stress, we would not be modern human. So a sort of cartoon, but to the rational beyond certain stress metrics, let's envision ourselves in a scenario akin to that of our assessors. A situation similar to the one shown in the figure is fortunately not very frequent today, but the specific stress reaction is identical. Let's imagine entering a cave and meeting a predator. What happened to our organism during the fight rest? The vision of a real or perceived danger trigger a whole series of psychophysiological reactions within us. One of the hallmark features of the fight or flight response is the activation of the stress response system, which include the hypothalamic pituitary adrenal axis and the sympathetic adrenal medullary axis. When the brain perceives a threat, the hypothalamus sends signal to the pituitary gland, which in turn stimulates the adrenal gland to release adrenaline and cortisol, as the stress hormone into the bloodstream. A subsequent reaction organized to prepare the organism to fight or flee. The muscle contract ready for action, breathing increase to bring oxygen, and at the same time, digestion slow down. The liver release glucose for energy. Furthermore, and there are commonly used metrics in stress evaluation, the heart rate accelerate to bring blood to muscle and tissue. Sweating increase, which is necessary for thermoregulation, but also to facilitate slipping from the grip of a possible predator, if we think about this. and the pupillary diameter increased to gather more peripheral vision useful for identify escape routes. Let's delve into the metric useful for analyzing stress. So, EEG signal. A typical electrocardiogram trace is characterized by several peaks known as P, Q, R, S, and T, each corresponding to the activity of different regions of the Earth. One of the key metrics related to heart rate is the distance between successive R peaks, referred to as RR intervals, expressed in milliseconds. A lower value of RR intervals indicate a higher heart rate and typically signify a more stressful situation. Another important metric derived from RR is heart rate variability, which provides into the distribution of RR intervals. This reveals whether they are evenly distributed or more variable. Metrics, for example, PNN 50, PNN 25, and other are commonly used to identify heart rate variability. So, a higher and less variable heart rate is directly associated with stress. As cited above, variation in the skin related to the sweat activity is another useful signal to detect and monitor stress. We can extract two distinct components from the raw galvanic skin response signal. First, there's the tonic component, which manifests as a slower response and is linked to the baseline activity of the sweat glands. Secondly, there's the phasic component, which is associated with stress. This phase exhibits more rapid fluctuation, which each stress-related event identified as peaks. From these components, various metrics can be derived. For instance, the time taken from the onset of the peak to its maximum value, known as rest time, and the time it takes to return to the baseline level, referred to as recovery time. The amplitude of the peaks, expressed as a measure of conductivity, microsiemens, represent the magnitude of the stress response. Despite the relative simplicity of the obtained GSR signal, these metrics are very effective to define stress levels. Relate methods from eye tracking technology offer valuable insight into real-time stress detection. One crucial metric is pupil diameter, which tend to increase in stressful situations. Additionally, saccades, rapid eye movement between fixation points, provide significant indicators of stress. Fixation duration and location are also informative metrics, with prolonged fixation identify heightened focus of distraction depending on the context. Furthermore, a blink rate serves as a proxy for stress, which include blink frequency associated with elevated stress levels, but also depend on the level of the concentration and the water condition. All these metrics and water collective offer a comprehensive understanding of responses, enabling timely intervention and tailored support to mitigate the adverse effect of stress in various domains. By leveraging these metrics, individuals and organizations can proactively manage stress and promote well-being. So, this slide shows some of the metrics for analyzing stress from the brain EEG signal. The EEG signal is a vital tool in stress analysis, offers several metrics for assessment. For example, a difference in theta seems to indicate a different stress level. In particular, is directly correlated with the level of stress. Alpha band power seems to be inversely correlated to stress, with a lower alpha activity in the more stressful situation. Conversely, an increase in beta band power is typically linked with heightened alertness, cognitive engagement, possibly suggesting elevating stress levels. Also, the beta to alpha power ratio serves as a comparative measure between state of arousal and relaxation, with higher ratio indicating greater stress. I added a slide to describe alpha asymmetry between the frontal channel, perhaps a bit less intuitive metrics. The typical but not the only channel used are the frontal channel F3 and F. Alpha symmetry is calculated at the difference of the logarithms of the alpha power of channel F3, left channel, and F4, right channels. Research seemed to demonstrate that during a stressful situation, alpha activity increased in the right frontal lobe compared to the left, having a negative final value because of the logarithm. Vice versa in non-stress situation. These are some, but not the only metrics used in research to evaluate stress. Well, now that we have aware of the metrics used in stress analysis, let's imagine putting our hand on a practical case of Industry 5.0, an analysis of collaborative robotics scenario, and it's in particular the impact of programming a cobot operate on stress level. In practical terms, I will dive into a recent project of mine and my colleagues that was presented at HRI conference in Colorado. The project resolves around SenseCobot, a multimodal dataset consisting of psychophysiological signals, including EEG signals, and subjective evaluation gathered from 21 operators engaged in cobot programming tasks. The dataset, freely available and hosted on a Zenodo repository, is meticulously structured to help research for human-robot interaction community, but also the whole scientific community. SenseCobot serves as a valuable resource for researching seeking to delve into the intricacy of human-robot interaction by providing rich, real-world data that encapsulate both objective physiological responses and subjective perception. Furthermore, the accessibility of SenseCobot making it a valuable tool for researching, looking to explore a wide range of research questions within the realm of human-robot interaction, for example, investigating stress pattern, cognitive load, emotional state, or user experience. Now, Antigrash, what is a cobot and why is it important in human-robot interaction and in general in the context of Industry 5.0? A cobot, the name for collaborative robot, is a type of robot designed to work alongside human in a shared workplace. Like traditional industrial robot, without typically caged off from a human worker due to safety conscience, cobots are designed to be safe to work with. Cobots as the UR10 with 60 degrees of freedom showing figure possess several notable characteristics that make them valuable in several industrial contexts, such as safety toward humans, user-friendliness, flexibility, and adaptability. That feature enable cobot to collaborate with humans in several industries, such as manufacturing, healthcare, and logistics. Despite that, the best synergy between human and cobot is achieved when several factors are satisfied. So if we think about collaborative robotic task become a perfect example to test the paradigm of Industry 5.0, human at the center. The technology should not cause stress to the user, but rather enhance its ability and improve its safety. Highly and efficiency and technological cobot that lack the characteristics necessary for correct synergy with the operator would be useless and be detrimental to productivity. There is a growing prevalence of cobots being employed in various industries, as shown in figure. The US market for collaborative robots is constantly growing, valued at 1.23 billion in 2022 and projected to grow further in the future. It's highly explanatory of the role that cobots have and will increasingly have in industrial tasks, but not only. Cobots are capable of carrying out tasks autonomously and without precision but need to be programmed by a human operator. For cobot programming, procedure and movement can be defined in various ways, such as using a teach pendant, which is a simple and intuitive programmer interface as depicted in figure. The program have a block-like structure of the Scratch type language. Or in free drive mode. With this last mode, the operator can manually move the cobot arm through a sequence of movement, the cobot can memorize this trajectory that can be replicated later. These are some of the programming techniques other are classical script-based programming. So our experiment was to replicate a real-life scenario when an operator of Industry 5.0 interacts with a cobot for the first time. The experiment was organized as follows. An initial learning phase in which the operator undergoes training in cobot programming by executing a series of tasks of increasing complexity. Notably, this phase did not involve wearing sensor and there were no constraints such as time limits or error recording. Following the initial learning phase, sensors were placed on the participant and a baseline was established to ensure a reference level for the recorded signals. Participants watched a series of emotionally evocative videos. Subsequently, participants now equipped with sensor proceed to complete the task introduced during the initial learning phase. Additionally, they perform an additional concluded task, task 5. To this phase, real-time recording captures signals, error, and reaction, providing valuable data for stress analysis. Currently, with task execution, participants complete a brief subjective evaluation using NASA TLX subjective questionnaire. For more comprehensive detail and descriptive video of each task, interested party can refer to this video already present on the SenseCobot on the Zenodo repository, where additional information and resources are available for reference. In particular, the detail of the cobot programming necessary for the execution of each task. In task 1, it has been asked to operator to program the cobot to move the arm between two designed points, A and B. I highlight on a sheet of paper on the work surface a very simple beginning task to familiarize with the cobot. In task 2, it has been asked to maneuver the cobot arm among 3 designed points. In task 3, it has been asked to maneuver the cobot arm to an arbitrary height from point A, and then gradually move toward point A while maintaining its perpendicular orientation to the work surface. After a short pace, the cobot should ascend again to point A. So the objective of this task, task 4, was to pick up a script located at point A on the work surface and perform a placement action using the cobot gripper. It has been required to grasp the script, elevate it, and subsequently deposit it at point. This last task, task 5, not already shown during the learning phase, encompasses all the previously acquired commands. It has been asked to manipulate a box, initially on a predetermined spot on the plane. Following this, it has been required to elevate a robot-like arm, slightly close the grip, and create a continuous boundary at a consistent place, a sort of gluing procedure. The scope of our research is now to monitor stress during this procedure, cobot programming task described above, using an Enobio EEG helmet. So now a closer look at the EEG helmet setup and the EEG analysis more detail that I used. The setup shows for the sorry, Enobio sensor was the standard 1020 configuration with a sampling frequency of 500 Hz. We use a cable connection and the use of NIC2 software connected with a different software that is iMotion. This software allows synchronization of different biosensors such as Enobio and export a raw synchronized CSV file for a signal recording with their respective sampling frequencies. All these data frames are now racing and subsequently extraction of the main metrics. So in these EEG graph represent real data obtained from our experiment, looking at the red halo, the ocular EEG channels. A dynamic cobot programming task includes movement of the subject and action of interaction with the cobot. It is certainly not the usual clinical static scenario for using EEG. However, one cannot imagine simulating a rest situation while keeping the participant static. So for example, in the blue arrow, we see a probably bad channel in which the contact is temporarily lost. Dynamically tasks meant that there were frequent movement, loss of either electric contacts, and loss of interference. Therefore, the process of cleaning the EEG signal is crucial for accurate analysis and interpretation of stress-related data. Clearly, the EEG signal involves several steps to remove artifacts, noise, while preserving the underlying neural activity of interest. One common source of artifacts in EEG recording is movement-related artifacts who can destroy the signal and obscure meaningful activity. That artifact can arise from muscle contraction, a movement, and other external source of interference. This figure shows the power spectrum in a signal obtained from a participant from this experiment, not already preprocessed, obtained during a task, included in a frequency band of interest in which the metrics that can be used for stress analysis are found, that is, theta, alpha, and beta frequencies band. Each one of the lines of the spectrum correspond to the power spectrum obtained from an individual channel. The presence of a unusable channel caused by motion artifacts or loss of contacts, also called bad channels, are already identified as a line of the spectrum that most the average channel behavior. It is therefore outlined that the preprocessing of the EEG signal is fundamental for correct analysis and interpretation of EEG signal, especially in very dynamical tasks such as the one in the industrial context. Here a proposal outline my approach to analysis EEG data from this experiment, which I employed personally but recognized as open to refinement suggestion. I use Python along the MNE library tailored specifically for EEG analysis. Initially, the raw EEG signal was downsampled, a step taken to alleviate computational demands. Next, a bandpass filter is employed for noise reduction, effectively eliminating high frequency interference and extraneous frequencies beyond our areas of interest. Subsequently, using the kurtosis method, we identify problematic channels, also called bad channels, caused by motion artifacts, big motion artifacts. Following this, an independent component analysis is implemented to target and remove artifacts stemming from motion, ocular movement, and other electrical sources such as cardiac or muscular activity. Ultimately, this process yields the power spectrum density for each channel within their respective frequency band of interest, alpha, beta, and theta for this experiment, for an epoch of 5 seconds duration. So, possible strategies. Everyone is aware of modern artificial intelligence technologies for classification. Certainly, beyond the traditional approach of extracting metrics, analyzing signals and data, and using statistics, it could be useful to use machine and deep learning techniques as implementation or in parallel. However, to use a supervised model to classify signal as stress or non-stress, or otherwise the data need to be labeled. In some classical example, this task is relatively easy, cat or a dog. But if we reflect, the labeling task will be complex, as normal acute stress cannot be classified objectively, as for example, other pathological condition diagnosed medically, for example, epilepsy, cardiac arrhythmia. In fact, a state a stress or no stress in situation of acute stress, but not pathological conditions such as, for example, post-traumatic stress disorder or other clinically identified stress pathology, it may be difficult. Will you be able to classify an operator state as more stressed than a +1, stressed 10, and then stressed 5? How to do this? My strategy, the simplest, I think, the strategy we used in this job was to ask the operator itself. In fact, it is important to evaluate the subjective perception of stress, considering the subjective personality, its cultural bias, and its psychophysiological state. To ask the user in an analytical way to obtain its level of perceived stress, a standard questionnaire, for example, NASA-TLX type, can be used, which include a series of questions on individual stress perception. By doing this, we establish a numeric score reflecting an individual perception of stress. Then we can create, for example, a binary classifier, stress or no stress, depending on the score. This approach was used to label a SenseCobot dataset in a simple binary classification. It can be adapted to create, for example, a multi-classification task with windows of score. Summary, investigating accidentally subjective conditions such as stress is intrinsically difficult. Necessary to use a multimodal approach, collecting as many biological signals as possible with advanced biosensors. The goal of creating the SenseCobot dataset from the experiment of human-robot collaboration described above was to integrate a lot of psychophysiological signal, a greater number that is currently available in modern stress-related dataset. In fact, SenseCobot incorporates facial expression, electroencephalogram, electrocardiogram, galvanic skin response, and others are recorded in time. Additionally, subjective evaluation was conducted through the use of standard NASA-TLX questionnaires. So, outside of the creation of the dataset, took care of analyzing the data. Well, at this point, from such a hypothesis setup, several research questions could be hypothesized. Some analyzed by me and exposed in an art currently under review could be whether there is an actual correlation between the individual perception of stress and the metric extracted from the signal. We could rephrase it as how much what I can get from signal analysis agree with what I perceive personally as stress. For this purpose, we wanted to enter into the detail by examining each individual perception process is illustrated in the detail in this figure. The metrics extracted from the various biosignals, including the EEG, were compared to the baseline. The answer to the question whether there is a variation in the parameter related to a resting condition is actually observed, or put another way, is the task indicative of being more stressful than a normal situation. Subsequently, we concentrate between the tasks to observe whether a statistically significant difference was observed in the metric between them. The null hypothesis is that a statistically significant difference is not observed in the metric obtained in the various tasks. A non-parametric postdoc test follow to observe which pair of tasks show a statistically significant difference, which instead has similar distribution. So, summarizing from the previous slide, what we obtained are the pair of tasks for which a statistically significant difference is observed for the matrix. That is, those of which we have evidence of actually different psychophysiological states that we can relate to different stress levels. Now we proceed to the comparison with the data from the subjective NASA-TLX questionnaire, and we count how much a variation in the response between the tasks is accompanied by a variation observed in the metric extracted from physiological signals. So, here are the results. The present box plot marks the percentage of agreement between the metrics extracted from the psychophysiological signals and the subjective assessments. The metrics obtained from the EEG signal highlighted in red. As can be seen, they are the most precise in defining stress. We can see theta power spectrum, alpha and beta power spectrum, and the derived metrics as the best in stress evaluation. But also, it should be noticed that however, trained from a signal really easy obtainable using non-invasive and low cost are those obtained from electrodermal activity of the skin, underlined in yellow. Sweat activity is a very good matrix for stress evaluation. So, okay, what is the purpose of all this, of stress assessment? Let's remember that we start from the context of Industry 5.0, in which human and the adaptability of technology to the user are the keys. Real-time assessment of stress using electroencephalogram and ultra sensor would allow the creation of adaptive platform or technologies. Let's think about one of the simple example, a smartwatch that when the operator reach a stress level, for example, it's monitoring my heart activity, want to change, there's a notification to the operator and want to change a task, perhaps preventing the operator from getting hurt. Other more complex example could be interfaces or entire platform that iteratively adapt to the operator until its stress level is minimized. This is the future. It may no longer be necessary to create and design an interface, but it could be made to adapt to the user conditions. Return to the beginning field, human-robot collaboration, collaborative robotics. The programming of the cobot can vary significantly depending on the process, task, or platform. For example, if I change the position of an object, I have to reprogram the entire procedure. Imagine instead that a series of if the condition change to this, if it vary to that, you connect the technology to the human, to the user, in particular to its biosignal and psychophysiological condition, with a feedback and interaction system with the hypothesize simple objective, minimize my stress level. An adaptive technology tailored to the user would be created. The same system that is tailored to the user and his needs. The collected raw data of the SenseCobot experiment from the experiment described above, labeled with subjective evaluation from the NASA TLX with the strategies described above, to foster also machine and deep learning application are organized based on signal, participant, and task in this dataset, SenseCobot dataset. SenseCobot dataset is made freely available at Zenodo repository, respecting the data maintenance and privacy policies of the subjects. We believe that multimodality of the SenseCobot dataset could provide a more complete source of the investigation of the user stress-related psychophysiological response in human-robot interaction context, but in general also in the Industry 5.0. So this is the last slide. I hope you enjoyed this lecture, and thanks to Neuroelectrics for the opportunity to share my research experience. I also hope the SenseCobot dataset can be useful source of investigation, research, and integration for the benefit of the entire scientific community. So thanks for your attention.
Simone, thank you very much for this presentation. We are not going to be stressed, but we still have time to take a few questions. So if anyone wants to ask something, please use the Q&A tool. And let me start with like a simple question. You were presenting the correlation between the questionnaire and the biosensors data. And there was the most agreement, my understanding was based on theta alpha EEG metrics. And to try actually to combine different metrics and to get, because the goal is actually to be closer to the subjective questionnaires in the evaluation, or it's not necessary. You want to have objective information. So this is one question. And the second, if you will combine this different information from different sensors, will you be closer to the subjective evaluation of the subject?
Okay, the second, I think that a correlation that is the next step will be more close to the subjective evaluation. Yes, about the first question, the problem is that we have to compare to a subjective perception of stress. Maybe the subjective perception of stress is not so, if we think, reliable, because we have bias, emotions, social implication in all this. But maybe the Nasati-Alix, the questionnaire, is worldwide recognized. First motivation for use it. And the second is that we have to correlate with the perceived level of stress. So maybe the metrics and the subjective perception are not in a great correlation, but the paradigm of Industry 5.0 is to adapt to the user perceived stress.
Okay, thank you. And another question, so regarding the common sources of stress in the human-robot interaction, and especially in the context of different robotic systems, so would you expect to have different sources interacting with industrial robots, with the service robots, with the medical robots, and like to extend this question, what are the key consideration in the experimental design actually to ensure that all this stress level are representative of a typical human robot interaction experiences?
So the problem for stress assessment in an industrial context is that we don't monitor a pathological condition, for example, post-traumatic stress disorder that change the structure of the brain. So the stress perception, I think, is task specific and situation specific. I think that in different situations, with different technologies, we have to expect to implement a different experiments setup. Personally, I found that, for example, there's a sort of pre-bias. There's some level of stress beginning the cobot programming because we don't have the knowledge of the technologies. The cobot may be afraid us, and we don't expect the reaction. So I think that there are the most bias for stress that cause stress when one interact with a cobot for the first time.
Okay, thank you very much. So yeah, from the longitudinal point of view, like you were measuring different time of different time points, the stress level and the effect in the continuous exposure to the stressful interaction. We are not there yet for the like mental health and productivity evaluation. My understanding is that right now we are planning to do this having one-time picture and not yet like longitudinal evaluation. Perfect. I think we are over time a little bit, so thank you very much for the presentation. This was really very, very interesting. Thank you everyone for joining us today, and you've got the link, the QR code where you can get actually the raw data if someone is interested, and you can also write to Simone to get additional information and find the publication as well. And I hope you're going to join us for the next webinar that will be actually in 2 weeks already with our guest, Dr. Matute and Meyer. We'll be talking about frontiers in neuromarketing with the innovative insights from IQS Neuro and Digital Lab. So you are all invited again. Please visit our webpage, neurolexis.com, where you can find more information about upcoming webinars. You can find also information regarding the past webinars. Thank you again. Have a great day. Take care and goodbye. Thank you, Simone. Thank you very much.